Let's now discuss support vector machines and the kernel trick. So in the last two sections we discussed SVMs, so their principle as separating hyperplanes, max margin hyperplanes. In the last section we defined the learning problem as convex optimization problem, which allows us to find a global optimal solution. Now we will combine them with the kernel trick, which will really boost the predictive performance of support vector machines. And this section really consists of two subsections, so the dual SVM formulation and the kernel trick. So the dual SVM formulation is an alternative formulation to what we discussed previously. And in particular, this has sometimes advantages over the previous formulation. And in particular, it will allow us to use the so-called kernel trick. And the kernel trick itself is a pretty general trick, which often allows us to boost machine learning algorithms. So in essentially, the basic idea is that machine learning algorithms can usually be improved by using first a nonlinear feature transformation before applying the algorithm, which is often effective but expensive because we have to compute a lot of nonlinear features. And the kernel trick essentially allows us to do this implicit and efficiently. And this is always applicable, or so as a general rule, this is always applicable when our learning algorithm works with inner products of our feature vectors. But more about this in a minute. So recall from the last section that this is our optimization problem for SVMs. And essentially everything which is in black here is the hard margin formulation. And then at the end of the last section, we had also the soft margin formulation, which is essentially all these green parts. So we had these lag variables and relaxed our constraints. So let's call this now the primal SVM formulation, because we will talk now about the Lagrange duality. And this will yield an alternative formulation, the so-called dual SVM formulation. And already this dual SVM solution or dual SVM formulation, this will be sometimes advantages over the primal SVM. But the main advantage is that the dual SVM will then only depend on inner products of our feature vectors, and therefore we will be able to apply the kernel trick, which is, well, a powerful trick to boost our machine learning algorithms. So in order to discuss the dual SVM, let's recap duality from optimization. So let's put aside SVMs for the moment and just look at a general optimization problem. Minimize some objective function, f, subject to constraints. And now our optimization variables are z. So in our SVM formulation, z would be w and b. But now we are considering a general optimization problem. And we have our objective and our constraint functions. And standard form really means that our constraints are given in this form. So we have constraint function smaller equals 0. So this is just what standard form here means. Well, we have our note. In general, an optimization problem often has equality constraints, but we won't need them here. So we will make things a bit simpler and omit them here. But well, objective, and we have our constraints in standard form. And yeah, so we will call this now, this optimization as, we will call this the primal problem, because we will talk about duality. So to discuss duality, we introduce a function which belongs to this optimization problem, the primal optimization problem. We will define a function, the so-called Lagrangian. And if we have this optimization problem in standard form, then the Lagrangian is very straightforward to define. So we just take our objective here, and then we take all our constraint function, and we just take a weighted sum of them here. And so the weights are given by the so-called Lagrange multipliers. So these are new variables, lambda I. So we have one variable per constraint here, and we have this weighted sum. Just take our constraints and weight them with our Lagrange multipliers and add them to the objective. So it's not really clear yet what this Lagrangian really does, but this is like straightforward. So if this is our problem, this is our Lagrangian. These lambdas are parameters or variables these Lagrange multipliers, and we will ask always that they will be larger or equal to 0. So they must be non-negative. This is something we will enforce here. And the Lagrangian depends on the primal variables, z, and also on this Lagrange multipliers. And this boldface lambda collects all the Lagrange multipliers, lambda I. So, and we will see how this can be used on the following slide. Okay, so here's our problem again, our optimization problem, and here again our Lagrangian. So this L, Z, and lambda. Let's now take the Lagrangian and do something useful with it. So we take our Lagrangian and let's now first maximize over lambda. So we maximize our Lagrangian over lambda, and so we are actually maximizing out lambda, and so this will yield a function which will now only depend on z. And let's give this function a name, let's call it L primal. So we are maximizing out lambda and we will have this L primal z. Now I claim if I minimize this new function L primal over z, then this is perfectly equivalent to this original problem. And can you see why? So actually I will tell you why. So it's best to put yourself into a position that you are this maximizer here. So essentially I give you this Lagrangian and I pick z. And you are allowed to pick lambda. And your task is to maximize lambda. Now figure that z is now a feasible point. So recall, feasible means that all the constraints are fulfilled. So z is a feasible point. This means all the GIs are smaller equal 0. So they are negative or at most 0. So if you're in control of lambda, you cannot control this part, you cannot control this part, and if the point is feasible, all these guys here are negative or at most 0. And your task is, well, maximize. And you have to respect these constraints that all the lambdas are positive or at least 0. So if you have to work with these g's, which are all negative, the best you can really do is to make the whole sum here 0. So for example, you could pick all the lambdas equal 0, then this would be 0, so you can always achieve this, but you cannot become larger than 0 because all these guys are negative. So for a feasible point, the best you can do here is make this go away, and what remains is the objective function, the original objective function. So this was assuming a feasible point. Now assume an infeasible point. This means there's at least one constraint, one I, where this is larger than 0, strictly larger than 0. And now you're in control of the lambdas. Now you spot here a guy who is larger than 0, and you need to maximize. What do you do? So one of the GIs is larger than 0, a tiny epsilon maybe only, but you just can take the corresponding coefficient and drive it to infinity. So you can now make this whole sum here infinite. So to wrap this up, a feasible point will just yield fz. So this guy here, so this function L primal, for a feasible point it will be just identical to objective. And for an infeasible point it will be infinite. So therefore if we minimize over z, so any infeasible point here will yield infinity, and a feasible point will yield the original objective. So we see this is indeed equivalent to solve the original problem. So this was fun, but we can also do something different. So like we defined this L primal function by taking the Lagrangian and maximizing over lambda. Let's do the opposite. Let's minimize over z instead. So we switch lambda against z and maximization against minimization. So we are now minimizing out z. So we take the min over z, and this gives us a new function. Let's give this another name, L dual, and this will now depend only on lambda. Now I claim for any lambda you want to pick, this function is a lower bound of the optimal value of your primal problem. And can you see why? And again, I tell you why. So here we have the Lagrangian, and the Lagrangian, so this L dual is just the minimum over the Lagrangian. And as long as we have at least one feasible point, so this feasible point will give some value for f, and the feasible point will give a term here which is only negative, and for any lambda larger equals 0, so we still have here the constraint that lambda must be larger equals 0, this term will be negative. So this will be smaller than the minimum. So for any lambda, this will be smaller than the minimum value of the primal problem. So this new function is now for any lambda, this is a lower bound. This is a lower bound for the original problem. And therefore we can now also maximize over lambda. So any lambda will give a lower bound. And if we maximize over lambda, this will be the best lower bound. So any L dual is, for any lambda, this is a lower bound, and we can maximize, this will give the tightest lower bound, the highest lower bound, the best lower bound. And this thing here, maximizing this L dual, is called the dual problem to this problem. So this is actually what the dual problem really is. It's a lower bound, and essentially we are trying to find the best lower bound. So again, L dual for any lambda is smaller than L primal from Z, and also therefore maximizing L dual gives a lower bound and the best lower bound of the primal problem. An interesting observation for convex problems is that the primal and the dual are tight. So essentially their optimal values are the same. So if we maximize the L dual, this is the minimum of L primal. So this is something which happens in convex problems. And in principle, the main story of duality ends here. This is already pretty useful. So it's a lower bound. The duality, or the dual problem, gives us a lower bound. And this is already pretty useful. So say we have a point Z, and we compute the objective of Z, and we find it's 17. And you want to ask yourself, is this good or not? And maybe sometimes you are able to solve the dual really efficiently, and you find out, well, this dual gives you so optimizing the dual problem gives you 15. So now you know that actually you are at most 2 off of your optimal value. So this is already useful, but sometimes it even happens that the dual solution also provides a solution for the primal. And for SVMs, this actually happens, as I'll show you next. So here is again our support vector machine problem. And this is now formulated as hard margins on no slack variables, no relaxation of the margin constraints. We do this for simplicity, and I will later show you there's only a very minor tweak downstream. So the same analysis actually goes through with the soft margin as well. And it's actually downstream, it's only a minor tweak, and I will show you this later. So here again is our primal problem, our support vector machine problem. Check back with the last section that is indeed the same. So I slightly rewrote it. So like recall it's 1/2 and the quadratic norm. And I just rewrote the quadratic norm as W transpose times W. So this is the quadratic norm. And I also rewrote the margin constraint slightly so that we have this standard formulation. So this Lagrangian asks for the standard formulation that the constraint function small equals 0. So I just reformulated this here. And if we have our problem in this standard form, then the Lagrangian is very easily compiled. It's just copy paste. We take the objective, put it here. We take the constraints and sum over it times the Lagrange multipliers. So lambda I, Lagrange multiplier for the ith margin constraint. So very straightforward, just copy paste, and this gives us the Lagrangian. So we will work now with this Lagrangian. So I put it again here. This is our Lagrangian. And recall, we want to compute this L dual function, and we want to minimize out our primal variables. These are the W's and B. And if we look at this objective here, or at the Lagrangian actually, we see W appears in a quadratic function, and here linearly, and also B linearly. And therefore, the whole Lagrangian is convex in W and B when we fix the lambdas. When the lambdas are fixed, this Lagrangian is convex in W and B. So X is given, this is the data, Y is given, W and B we want to minimize. Lambda is also fixed, so we just can now, since this is convex in W and B, we can take the derivative, the gradient of lambda, and set it to 0. So let's do this. So first we take the gradient with respect to W. So the gradient, so nabla W of the Lagrangian, which is just the vector of all the partial derivatives of our W's. And if you're not familiar with this, this is essentially exactly the same form as if W was a scalar. So this is W squared essentially, and if you derive this, then you have like this 2 coming down here, cancelling with the half, and what remains is W. So exactly the same recipe applies for vector derivatives or gradients. And here, so essentially W is a linear form with xi, so W goes away and only xi remains, and so the 1 goes away, B goes away because they don't depend on W, so we are left with the sum over lambda, y, and x, and this goes over the training samples. And so we want to minimize the Lagrangian with respect to W, so we need to set this to 0, and this immediately follows that W is now given by the sum of lambda I, yi, and xi. So and this is interesting. So xi is these are our training examples, and the yi the labels, and we have this lambda I. So we see that in an optimal solution, W is actually just this linear combination of our training examples, weighted by sample, by label and Lagrange multipliers. So the Lagrange multipliers together with the data determine the solution for W. So this is, we set the derivative of W to 0, and now we do the same for B, and it's easy to see the derivative of B is just this sum here, and this needs to be 0. So this is, B has disappeared, and now we are just left with essentially this constraint. Now we have a solution for W. Let's plug this into our Lagrangian. So we know what W should look like in terms of lambda. So if we plug in W here in the Lagrangian and multiply out, then we get this. So this red term here just becomes this red term here, and this green term here just becomes this slightly big term here. And if we reformulate, if we just, so this here becomes this sum, which is essentially the same sum here. It goes in with minus, so we are left with minus a half, this double sum over I and j. So I and j run both over all training examples, and we have lambda I, lambda j, yi, yj, and this inner product between ith and jth training example, and this sum over the Lagrange multipliers. So this is now our dual objective, and we have this constraint, and if we summarize this in an optimization problem, we get this so-called dual SVM problem. So now we need to maximize lambda, and this was the L dual. We got this constraint by minimizing over B, and the Lagrange multipliers need to be positive. So this is the dual SVM problem. And in principle, the dual just gives a lower bound, but as we saw previously, we also have a solution. So we can compute, if we have an optimal solution for lambda star, this also delivers an optimal solution for the primal. So we just saw W is given as this, so this linear combination of training examples. And it also turns out that the optimal solution for B is just given by this formula for any sample where lambda I is larger than 0. And the good news is that this is still a quadratic program and convex. So we maximize here, but it's a negative quadratic function, so this is a convex optimization problem. And essentially, same hardness as our original problem, which was also a quadratic program. I promised you, so this is our problem. And if we want to include our slack variables, so where we trade off our slack variables with this trade-off parameter z, the only thing, so this was for hard margin, and if we have the soft margin with this trade-off parameter z, the only thing which changes is that we have now also an upper bound for our Lagrange multipliers. So I don't do the derivation here, but essentially, believe me, the only thing which really changes is that we have another constraint for our Lagrange multipliers. So interesting, we can now also solve SVMs in the dual, essentially. And this is already pretty useful sometimes. So if you look at the sizes of these different optimization problems, so the primal was depending mainly on the number of features, because we had our weight vector explicitly in the optimization. So, and the length of the weight vector depends on the number of features, of course. And in the dual SVM, we have this double sum ij, which run both. So we run over all pairs of training examples, and therefore the size of the dual SVM problem is already n squared, where n is the number of samples. Now figure that the number of features is huge, but the number of samples is small, then the dual SVM can be expected to be cheaper. And vice versa, if you have a really large number of samples, then the primal might be more beneficial. However, the big topic here is actually the kernel trick. And so an interesting phenomenon of the dual SVM formulation is now the whole problem is only defined via these inner products of training examples. So the ith and the jth training example. And therefore, the dual SVM essentially unlocks the kernel trick for us, which we will discuss next.